also got a list of attendees. If you'd like to put your name on that list, then we can keep you in touch with this regular seminar series. We've tried to institute this seminar series to give exposure to folk both within QUT and certainly outside in industry about what's happening in academia. And this is going to be a regular occurrence, so if you can put your name on this list in the front here before you go out, then we can put you on a regular list. And so, to the affair of the day. John Barry, Dr. John Barry will be presenting today. John's got experience in both industry and academia, outside the country and inside the country. In fact, John and I have had the pleasure of working together in a little company that I founded. So I certainly appreciate John's talents and ability, which range from appreciation of material in theory and experimental sense, as well as a good grasp of microscopy, which is pretty handy for a materials-orientated person. So the talk today is about concentrated solar power, and John will be discussing different aspects of that. This is going to be quite pertinent, I feel, maybe in the weeks and months ahead. There's a number of programs that have been floated, potentially funded by the federal government, assuming that they can be undistracted from fighting over question time. And these decisions, should they be made, will precipitate in a major solar activity, potentially, in Queensland. So perhaps a number of people in this room will be involved in that. So without further ado, I'll hand over to John. Thanks.
Might use a microphone, I think. Yes, that seems to be probably better, since it's a big room. Thank you, Richard, for the introduction. What I'm going to do today is talk in very general terms about concentrated solar power, to describe what I know of the field and the sorts of things that are happening in the world, in particular in Spain and in the United States, through the concentrated solar power. And at the end, I'm going to talk about how that might go forward in the future. The thing about it is that concentrated solar power is getting the heat, getting energy from the sun, and there's lots of energy coming from the sun. That is, if we know how to use it, we can use it to replace coal or oil as well, if it's used carefully. So, at the moment, the industry of concentrated solar power doesn't really exist. It's more like demonstration plants, and it's quite rudimentary in that sense. What, if you would compare it to photovoltaic energy, which is much more mature, it's very much earlier in its development stage. So, but you can still see what the possibilities are, and there are many possibilities, a whole variety of things that can be done with using the sun, concentrating the sun's energy to generate high temperature, which is really what it's all about. So, so that's the topic of what I'm talking about today, using heat energy from the sun. And what I'm going to talk about is the energy group at QUT, naturally. The group of people who are here who are working in the area of energy. I'm not going to talk about everyone, and I apologise to those of you who I don't mention. And then I'm going to talk about how you use heat from the sun, the various temperature ranges and the kinds of things that you might use it for. And then talk about the solar resource. How much is there? Is there enough to really replace coal and oil? And then I'm going to talk about types of concentrated solar power, the various techniques or technologies, including parabolic trough, which is the most common sort at the moment, and Fresnel reflectors, which is a technology developed in Australia, and dish reflectors, or dish Stirling, usually because it's got a Stirling engine attached to it, and solar power towers, and also talking about the issues of storage. And then I'm going to give some examples which are really at the high end of temperature to demonstrate that actually you can do some pretty fancy things with the sun. And then I'm going to tell you about the improving efficiency and cost effectiveness, which is that where it needs to go in order to become practical and useful, and how that can be integrated into existing technology and where the future will take us. So the energy group at QUT is led by Professor John Bell, and his interests, among other things, materials, buildings and energy systems. And we have Professor Gerard Ledwich here as well, who's into power electronics and smart grids and other things, and Associate Professor Farouche there, who's also into power electronics. I won't go through everyone, but you can see there's a mix of people. There's people who do thermodynamics, who do chemistry, electrochemical, who do building design and energy efficiency and alternative energy, and nanotechnology and semiconductors and material science. And that's where I come in. Material science is my major area, and it is fairly clear, to me at least, that in order to make solar power more efficient, at least concentrated solar power, there's a need to develop new materials and new technologies to make it cheaper and more widespread, more effective. So what kinds of things can be done with heat from the sun? You're probably more familiar with the low temperature, below 100 degrees, which is solar hot water and that sort of thing. So you use flat detectors, flat collectors for that. And it also can be used for food processing and for house heating and for cleaning out beer vats and all kinds of things like that. So that's quite an advanced stage of technology. It's been around for quite a while. But as we go up in temperature, that's much more the development area. And above 100 degrees, you need to get into more concentrated solar, such as a parabolic trough. And that can be used for chemical production, for running some chemical plastics, polymers and things like that, which need heat for curing, and it can also be running air conditioning. So it seems crazy, but you can use heat to make air conditioning, and if anyone is old enough to remember the gas refrigerators, would know that you can use heat to make things cold. It also can be used in food and textile processing and various chemical processes I already mentioned. So if we go above that, we can get to a case where we can start to add energy to gases, like take a fuel and add energy to it by reforming it. So you can take like a coal gas and reform it to make something which has got more hydrogen attached to it, and therefore make it more energy, get up to 30% more energy out of that fuel. So that's 300 to 600 degrees, you can start to do stuff like that. And also run Rankine systems, not necessarily based on steam, but perhaps only on organic gases, but you can start to generate electricity in that range, 300 to 600. And at the top end also generate through high pressure steam, superheated steam. For that temperature range, you can still use parabolic trough, and parabolic dish also works in that temperature range, and the central towers. And above 600 degrees, you tend to be in the range where you need to use a central tower. It's pretty much an exclusive area of central towers. And in that area, you can do, of course, steam production and electricity production, and melt metals for steel and, or maybe not high enough for steel, but even there it's possible. Steel and metal, aluminium production. Certainly there's a lot of energy used in making aluminium, and doing it using the sun would be much more, well, if it can be made cost effective, it would be a much better use of the technology. So, as well as the method for concentrating the sun, there's different ways of transferring the heat from the point of concentration to where it needs to be used to transfer it. And at lower temperatures, you just use water. But as you go up to higher temperatures, you need things such as oil, which is a high melting point, high vapor point, I should say, and molten salt. And molten salt are fairly familiar salts like potassium nitrate and sodium nitrate, salts that are solid at room temperature but are quite fluid and runny when they're above 250 degrees or so. So that makes a very good medium for transferring heat. But also, surprisingly, and more people are working on this, air is a very good transfer medium because it's much easier to manage. You just have to pump a lot more of it through. And again, there's the issue of storage. Now, this is where concentrated solar energy really wins, because storage of heat is cheap, whereas storing electricity is not cheap. And also storing electricity often has an environmental cost with batteries having to make them and dispose of them and so on. So this is where concentrated solar has its advantage in a sense, in that you can easily store the energy. And for low temperature, like in buildings, below 100 degrees, you use the bricks in the building to store energy, and one of the reasons why mud brick houses are so comfortable to live in is because thick mud bricks store energy quite well. So if you're in a desert where it's hot in the day and cold at night, it evens the temperature out quite well. Also, of course, mud bricks insulate the inside from the outside, but their thermal mass is quite a significant contributor to the storage of heat and cold. Also, in the building industry, they use phase change materials to store energy. They have materials that they build into the walls, which have a phase change around 30 degrees Celsius. So above that it melts, like something like wax, for example. Above that temperature it melts and then soaks up heat, and below that temperature it cools and gives the heat back. So it makes an effective way of balancing temperature in a house. Above that temperature you can use oil or molten salt or rock as a storage material. So these things can store quite a lot of energy very cheaply. So is there enough solar resource to do all this and to supply all the energy needs in Australia, including everything, not just electricity, but fuel and heating and industrial uses of energy? I make an assumption that you can use 6 hours of sunlight a day, and if you had 10% conversion efficiency, it would take an area of 85 by 85 kilometres to collect that amount of energy from the sun. And I've drawn on the map of Australia what that looks like. It's this little blue dot here. So to supply Australia's energy needs from the sun is quite feasible, certainly in terms of the amount of energy that's coming in and landing on Australia. And especially in somewhere like Western Queensland, where the little blue dot is, it's very dry and quite sunny. And it has the advantage of also being politically stable. In Europe, they're looking towards the drier places near Europe, North Africa and Saudi Arabia and places like that, to put solar energy plants and to transmit electricity and so on from there to Europe. The disadvantage of those places compared to Australia is they're not particularly stable politically. And this will become more and more an issue, I think, in the world as we go forward. Not only having a trained workforce and availability of sun, but also political stability will make a difference, especially in this world which is so quickly changing. So my message here is Australia is well placed not only to supply its own energy needs, but also to become an energy economy based on the sun. And you think, well, how can that be? How can you just transmit electricity to Indonesia or somewhere else from Australia? Well, it's a long power line, that's for sure, and that hasn't been done yet. But there's also the possibility, which I'm going to talk about later, but I'm not going to talk about now, the possibility of revitalising regional Australia, because where the energy is where you put your factories and your processing plants, out there in the desert, where the energy is, so you don't have to transmit it. That's a completely different way of thinking about infrastructure and a completely different way of thinking about industry.